On the last page, page 47, we figured out where the second derivative was 0, and then we made a sign chart for before and after that. And now we're just going to give that a definition. So whatever makes the first derivative 0 was called the critical number, but now we have something called a point of inflection, now that we're in second derivative world. And a point on the graph that is continuous and has a tangent line exist and concavity changes is called a point of inflection or inflection point. So really the two things that we're checking out of this fancy definition. An inflection point, first and foremost, makes the second derivative 0 and has concavity change. So we can make the second derivative 0 or really undefined, like we talked about before. We can make the denominator 0. And concavity changes. So we have to go from concave up to concave down or concave down to concave up. So those are the two things you're checking to be a point of inflection. Critical number, all it has to do is make the first derivative 0. Points of inflection in second derivative world have to do two things. Make the second derivative 0 or undefined, and then they also have to have concavity change. So now let's go back to our example from before and see, did this have a point of inflection? So do I have a number where the second derivative was 0 that also has concavity change? Let's see here. My second derivative was 0 at x equals 1, so that's my possible point of inflection. I'm not sure until I look at my sign chart. So if I look at my sign chart, the concavity does change from concave down to concave up, so that is a point of inflection. So yes, we do have a point of inflection. The x value is 1. So we already have that here. And to find the y value of any point, I just need to plug back into the original. So if you plug back into f of 1, that's how you'd get this answer here, into that long original function up top, x cubed minus 3x squared minus 24x plus 92. When you do that, your y value is 66. So let's use point of inflection here, and we will determine concavity and points of inflection of the function f of x is the cube root of x, something we found increasing and decreasing for before. Now let's find completely new information, but with the same type of steps. So first step, take the second derivative and set it equal to 0. So here I'm going to take the first derivative, and I want to remember this is the same exact thing as x to the 1/3. So my original function was x to the 1/3, so the derivative is 1/3. X to the 1/3 minus 3/3 is negative 2/3. And then my second derivative, I'm going to bring down my power again. And I'm going to write these fractions out. I'm going to keep my 1/3 out front. And I'm bringing down my power of negative 2/3. X to the negative 2/3 minus another 3/3 minus another one would be giving me a negative 5/3. So I want to set this equal to 0. It would be easier to do if I simplified it. So I'm going to multiply these fractions together. So multiplying the top together, 1 times negative 2 is negative 2. And the bottom, 3 times 3 is 9. And then I have x to the negative 5/3. Well, that's a negative exponent, so it must belong in the denominator. So I'm going to write x to the 5/3 here. So I want to think about what would make my second derivative 0 or undefined. Well, I can't make the numerator 0, so nothing's going to make this 0. I need 0 divided by something to be 0. I can only make the denominator 0. To make the denominator 0, I'd have to multiply 9 by 0. So it must be 0 being raised to the 5/3. So x equals 0 is a special number because it makes f double prime undefined. I make the denominator 0 there. But I'm not going to call this a point of inflection yet. I need to make sure it actually is a point of inflection. So it's a possible point of inflection. The one thing I need to check now is, does concavity change? If it doesn't change, if it's always concave up, then I would simply say there's no point of inflection. So I want to see, does concavity change? Because I'm asked for points of inflection and where is it concave up and concave down. So my possible point of inflection is at 0. And that's a possible point of inflection because it makes f double prime undefined. So I'm going to label it, this is my special number. That is the only place where I could have a point of inflection. And it's the only place where concavity could change. No other x value is going to be in my intervals. So if I look to the left of 0, I can plug in any number I want. Maybe I'll just plug in -1. -1 to the 5/3 is a -1. Times 9 is going to be -9. So I have -2 over -9. And remember, you don't need to plug in these values to find the answer. You just need the sign of them. So at the top, I have a -2, which is negative. And the bottom, I'm going to have a negative as well. So this interval is going to be positive. So before 0, I am concave up. After 0, I can plug in anything I want. I'm going to plug in 1. That's nice because 1 to any power is 1. So when I plug in to the top here, the top is still going to be -2, so it's going to be negative. And I'm going to divide that by 1 to the 5/3, which is 1, times 9, which is going to be positive. So I'm going to be negative here, or negative divided by a positive. So I must be concave down on this interval. So a rough sketch of what this looks like, it'd be concave up, switching to concave down, and wherever I'm in the middle of my concavity is where that second derivative is 0. So there's my x value of 0, be located there. So I do have a point of inflection. It does make the second derivative 0 or undefined, in this case undefined, and I do change concavity. So I do have a point of inflection at 0, and I would plug that into the original. So I would take the cube roots of 0, or 0 to the 1/3, which is just 0. Here's my x and my y value. Remember, we always plug into the original function to find the y value of a point. So I plugged in f of 0. We are concave up from -infinity to 0, and concave down from 0 to infinity.